All right, so now we're going to look at invariants for multi-parameter persistence modules. So the ultimate goal would be something resembling a barcode or a persistence diagram. And the persistence diagram is this great invariant for multi-parameter persistence the persistence diagram is this great invariant for persistence modules or filtrations. The goal would be to have something nice like that, something that gives us a topological summary of our data that sort of captures only the interesting information and gets rid of the noise while still being stable and efficiently computable. That's the ultimate goal for multi-parameter persistent homology. And we're still working on that to this day. So the first invariant proposed for multi-parameter persistence, and this was also really the first time that multi-parameter persistence was proposed in general, was a function from a paper from Gunnar Carlson and Afra Zamarodian, where they showed that there is no complete discrete invariant for multi-parameter persistence. So this is a bit of a letdown. In the one parameter setting, we have the persistence diagram, which is a complete and discrete invariant for multi-parameter for persistence modules. They showed that there is no such thing. Not only they didn't just say we couldn't find one, they said no such thing exists. And that's quite a shame because it would be very, very useful if there was a complete invariant, a complete discrete invariant for multi-parameter persistence. Now, they did propose a solution. They proposed the rank function. And so what this is, let's say we have a multi-parameter persistence module, and we're just going to look at the function that assigns to any interval, right? So if we pick a pair of points, A and B, and R to the n, and let's say A is less than or equal to B, this function is just going to assign to that interval the rank of the map, right? Remember, we get a linear map from the space at A to the space at B. And this function is just going to assign to that interval the rank of that map. And so in the 1D setting, this is equivalent to the usual persistence diagram. This captures the same information, but in the multi-parameter setting, they're not equivalent. Yeah, so this is sort of a half solution, right? It's an invariant. It loses information that we'd like to keep, but it's relatively computable, and it does give us a sort of topological summary of our data. So it is satisfying a few of the conditions we were looking for. Okay, and now there's perhaps a slightly easier way to think about the rank invariant, which is as sort of sliced multi-parameter persistence modules. So let's say we have this multi-parameter here really we're looking at this multi-parameter filtration, but applying homology, we get a multi-parameter persistence module. And the idea is we're just going to slice this. So imagine let's look at this red line here. And imagine we just restrict our multi-parameter filtration here to this red line. And what we'll get is just a one parameter filtration, right? And we can sort of vary the lines we choose, and we'll get a bunch of different one parameter filtrations, a bunch of different slices as we take different lines. So with this slicing, what we're doing is we're taking a multi-parameter filtration and we're turning it into something one parameter, where we can compute the normal persistence diagram along each slice. And so the collection of all of these persistence diagrams or barcodes is known as the fibered barcode, right? And so this is basically just taking multi-parameter persistence modules and turning them into something one parameter where we can work with them. And yeah, so this idea was first proposed, I think, in a paper by Claudia Landi and collaborators. And the data that's captured by this invariant is actually the same as the data in the rank invariant. So this actually captures the exact same data that the rank invariant does. Okay, so now let's look at what happens, as we vary the line we're choosing, right? So let's say we already computed the persistence diagram for this red line, and now we're looking at this blue line here. The idea is that nearby lines will have similar barcodes. And so we don't actually need to compute the barcodes, right? If we want to actually compute this invariant, you might think, well, that's going to be impossible. There are infinitely many lines. But it turns out that that's actually not the case, especially if, in particular, if our multi-parameter persistence module is nice, like this one is here, where it's sort of constant on a grid, then we don't need infinitely many lines. And also nearby lines are going to have similar barcodes anyway. And we don't actually need to compute the barcode for every line. We can use something called the Vineyards algorithm, which gives us a way that if our data set is very close to a data set that we've already computed the persistence diagram for, it gives us a way to compute the new persistence diagram in linear time from the old one. So this is something that can be used very effectively, and it is used in some multi-parameter invariants. And then the last thing is that the fibered barcode, so this collection of all of the lines is a stable invariant. And remember, the fibered barcode is equivalent to the rank invariant in terms of the data it captures. So this shows that, the rank invariant or fibered barcode is not perfect. It's losing information we would like to see, but it is capturing a decent amount of information, and it is a stable invariant, which is what we had in one parameter persistence. Okay, so let's look at what it means for the fibered barcode to be stable. Okay, so we looked at the bottleneck distance last time. We had matchings, right? So these were just bijections between the multi-sets of intervals. And the bottleneck distance is, we take the inf over every matching of sort of the cost of the matching, right? Given a matching gamma, what's the distance between, what are the two farthest apart points that are matched in gamma, and how far apart are they? That is the cost of matching. And then we're sort of taking the matching with the least cost, and that gives us the bottleneck distance. Right, and we have this right here, which is the bottleneck stability theorem. Right, if we have two persistence modules M and N, and they have barcodes I and J, then the bottleneck distance between I and J is at most the interleaving, or actually this is the isometry theorem. The two distances are actually equal. Last time we saw the bottleneck stability theorem, which is one side of this, which is that the bottleneck distance is less than or equal to the interleaving distance. That's the hard direction. The other direction is a bit easier to show. But it turns out that these two distances are actually equal, or isometric, really. And we can use this theorem here to get an analogous result for fibered barcodes, and to show that fibered barcodes are stable invariant. Okay, so the analog of the bottleneck distance we're going to look at is something called the matching distance. So here we're going to just focus on two parameter filtrations, two parameter persistence modules. We're going to let this curly L be the set of all lines in R2 with positive slope. It's important that we work with lines with positive slope, because if we work with lines with negative slope, we're actually not going to get a filtration at all. I'd encourage you to take a look at this picture right here and look at a line with negative slope and see how we get something that's not a filtration. Okay, yeah, so okay, so now if we choose a line, we're gonna call this M sub L. This is going to be the persistence module M restricted to the line L, and we're gonna let BML be the barcode of the persistence module restricted to L. So right, M sub L is a one parameter persistence module, so it has a barcode. We can decompose it nicely. Okay, and now the matching distance between fibroid barcodes of M and N is going to be this quantity right here. So we're taking the soup over all lines L, and this W sub L is a weight function. We'll get to that in a second, but for now, just ignore that W sub L. What we're looking at is we're taking the soup over all lines L. Right, so essentially we're maximizing over all possible lines of the bottleneck distance between the two barcodes of the persistence modules restricted to those lines. So basically we have these two multi-parameter persistence modules. Now we're slicing both of them along the same line, and we're looking at the bottleneck distance between those two barcodes, right? We're trying to match up bars. And so that'll give us some number. And now we're going to maximize over all possible lines L. Okay, but now we do need this weight function here. And this weight function, so we'll see on the next slide why this weight function is important. Basically this weight function here is just going to depend on the slope of the line we pick. And so if we have a line L that's has slope M, the weight is just going to be 1 over the square root of 1 plus M squared. Okay, and so now let's see why the fibroid barcode is stable and why we need this weight function to get stability. So let's say we have these two parameter persistence modules, and they're now epsilon interleaved. Okay, so the idea is that we want to take this epsilon interleaving between multi-parameter filtrations, and we want to turn it into an interleaving between their sliced persistence modules. So let's say we're slicing along this green line L right here. So we have right, so we're starting at M of A. We want to get a map from M of A to some point for N along this green line. Well, what we can do is we know that we have a map, right? Because M and N are epsilon interleaved, we know that we have a map from M of A to N of A plus epsilon. But now N of A, right? So basically, if we look straight up, this N of A plus epsilon is going to be less than or equal to N of A plus epsilon plus B, where B is this vector right here. Right, so A plus epsilon is less than or equal to A plus epsilon plus B. So we're going to get a map from N of A plus epsilon to N of A plus epsilon plus B. And that gives us the desired map that we want. And now it just becomes like a high school geometry problem of figuring out what is the distance between A and A plus epsilon plus B. And if we figure that out, we actually get that it is epsilon times the square root of 1 plus M squared, which is exactly the weight that we're dividing by here. And so that's why dividing by that weight is important. It's important to get stability. But now that we have this, we can just apply the bottleneck stability theorem and get that the bottleneck distance between the two sliced barcodes is going to be at most epsilon times the square root of 1 plus M squared. And now because we're right now for the fibroid barcode with the matching distance, we're dividing by the square root of 1 plus M squared. That cancels out. And so the quantity we're maximizing over is always going to be at most epsilon for any line we pick. And so that tells us that the matching distance is also going to be at most epsilon. Okay, so we've looked at a couple invariants now, and let's look at some algorithms for multi-parameter persistence. So the first algorithm, and the most widely used in practice, is Rivet. So this is a tool for computing and visualizing firebird barcodes. So essentially what Rivet allows you to do is input like a multi-parameter filtration or persistence module, and then you can select a line and it'll compute the persistence diagram of the module restricted to that line. And as you change the lines, you can see it change the barcodes over that line. Rivet is a bit slow for use in large data sets. This is an issue with pretty much everything out there for multi-parameter persistence. I believe this figure here is this O of n to the 8th is for this figure is if you're looking at augmented metric spaces, if you're looking at 0-dimensional persistence for augmented metric spaces, you get something that is O of n to the 8th time, which is a bit unfortunate, but it's just reality for working with multi-parameter persistence modules and multi-parameter filtrations. Right, and so this is what Rivet looks like. So like, let's just focus on this top left window here. What we're seeing is that we have this, there's this line selected, this blue line here. And we can see the barcode above it on the left. The barcode are those purple bars sitting above that. And then on the right is the persistence diagram. Of course, the persistence diagram and barcode are the same information, but it's just two different ways of visualizing it. Some people prefer to visualize it one way, others prefer to visualize it the other. Okay, so let's look at another invariant for multi-parameter persistence. And this is going to be based on the Elder rule. So the Elder rule is sort of, it's sort of a philosophical thing in persistence that oftentimes doesn't really get baked into the definitions at least explicitly, but is sort of philosophical thing that says that when two homological features merge into one, the older one is the one that lives on. So this is something that's implicit in the barcode decomposition. You don't have to actually enforce this. If you do the barcode decomposition, you will see this as a result. It's sort of it's not something we need to enforce. It's something that is sort of naturally happening. So let's look at an example here. So in this example, what we have, so we have the reals, and this is including into R2, so a 2-dimensional space. Okay, and then what we have is that this 2-dimensional space is then becoming a 1-dimensional space. But the way that that's happening is that these two features are merging together. It's not really the case that either one is surviving, essentially, but they're sort of merging together. And if we look at the barcode decomposition for this, though, what it's going to give us is that it's going to tell us that we had a feature that was born all the way at the left, and it died all the way at the end when it finally becomes 0. And then this feature that was born later dies first, right? When the two features merge, it's the older one that lives on, right? And so I do want to emphasize that this is not something we need to implicitly assume or enforce. It's something that sort of is a side effect of the barcode decomposition. Okay, and so this idea, though, can be incorporated into to give us an invariant for augmented metric spaces inspired by the Elder rule. So we're not going to go too into the details of this invariant, but This invariant it's a more robust invariant than the fiber barcode with one. So yeah, I should mention that this invariant here, elder rule stair codes, it's very specific. It only works if we're working with augmented metric spaces and zero-dimensional homology. So zero-dimensional homology we can think of as clustering. So this is still quite useful, right? It tells us information about clustering for augmented metric spaces. But now, when we're in that setting of zero-dimensional homology and augmented metric spaces, this invariant here, this elder rule stair codes invariant, captures more information. That's what I mean by more robust here. It captures more information than the hybrid barcode. And it's also much faster to compute. These can be computed in O of n squared log n time, where n is the number of simplices. So much faster to compute and yeah, much and captures more information. But the downside is that it's more specific. And yeah, one very nice thing about elder rule stair codes is that they are able to determine whether or not certain persistence modules are interval decomposable. This is something that the rank invariant can't do. Of course, again, I want to emphasize that this is just a specific case and not in general. But, or really, elder rule stair codes only apply to a specific case. But this is something that the rank invariant can't do, is determine when a persistence module is interval decomposable. Okay, the next invariant we're going to look at is something called the vineyard decomposition. And so the idea here is it's essentially the same idea as the hybrid barcode. We're going to look at a bunch of slices. Only now we're going to essentially, as I was mentioning earlier, if you take nearby slices of lines, the persistence diagrams, right, the barcodes are also going to be nearby. And so, and actually it's a bit more than that. It actually gives us a way of matching up bars in the barcodes of nearby lines. So essentially, so let's look at this box in the lower left here. And we have all of these black lines slicing our persistence module. And let's say we get these green bars in these lines that have the green bars. The Vineyards algorithm is going to let us actually match those up and say that this green bar is the same as this one here, is the same as this one here, and so on. And we can also do the same with the blue bars. We can match those up. And now we can just take those bars that are all matched up and sort of separate them. And so what we'll get is these separate sets of lines here. Okay, and so this gives us more information than the rank function and fibered barcode. So this is a pretty nice invariant. And these have also been shown to be stable in a way. The next thing we're going to look at is multi-parameter persistence images. So these are built off of the Vineyard decomposition. And the idea here is that we want to turn this Vineyard decomposition into something that is, right, we want to turn the Vineyard decomposition into something that is a vector. We want to vectorize our data so that we can use machine learning and statistics and stuff like that. And the idea behind it is that basically we're going to place a Gaussian over each bar in the Vineyard decomposition and sum them up. And then we're going to discretize the resulting thing. And that is going to give us a vector in Euclidean space. Once we have a vector in once we have vectors in Euclidean space, you can do machine learning stuff to them pretty easily, and statistics as well. Yeah, so we're not going to go too into this right now, but this is a tool that is used in practice sometimes. The next thing we're going to look at now is multi-parameter persistence landscapes. And so the goal here is pretty much the same as multi-parameter persistence images. We want to turn, we want to get a vectorize these things here. So we want to take our persistence, our fibroid barcodes and vectorize them so that we can fit them into a machine learning pipeline or look at statistics of them. So yeah, these are just constructed from the fibroid barcode. And these are less robust than the fibroid barcode. We're losing information. However, there is a way to modify them so that they do carry the same information. And yeah, multi-parameter persistence landscapes are stable, which is good. And this is what they look like here. Or rather, these are just persistence landscapes in general. We're not going to spend too much time on this. But yeah, they are another commonly used invariant. So yeah, now let's talk about statistics for a bit. So even in the one parameter setting, barcodes are not very well behaved from a statistics point of view. So even when we're working with just nice one parameter persistence modules, we can't necessarily define means between them. If they're yeah, this is something that's quite unfortunate, and there's not necessarily a good notion of means going on here. Persistence landscapes and persistence images are attempts to fix this issue. And so the idea is that we want to take our persistence diagrams, or whatever our output is, whatever our invariant that we're getting is, we want those to be vectors in Euclidean space. If we have vectors in Euclidean space, we can take averages, we can do principal component analysis, we can plug them into machine learning pipelines. There's all sorts of things we can do if we have vectors in Euclidean space. So that's the goal of these persistence landscapes and persistence images, is to give us something in Euclidean space. So these multi-parameter persistence landscapes are particularly nice from a statistical point of view because they obey a strong law of large numbers and a central limit theorem, which are two very important concepts in statistics. Okay, so now let's talk about the complexity of some of these algorithms here that we've looked at, the computational complexity. So the elder rule stair codes algorithm is the fastest, and it runs in O of n squared log n time. It also captures the most information, but it is the most specific as well. It only works on a very specific type of data set, right? It only works when we're looking at augmented metric spaces and we're interested in zero-dimensional homology. Now, this is a very important type because looking at persistence of zero-dimensional homology is closely related to clustering. In fact, it is just a form of clustering. So it is an important application, but it is the most specific. Rivet is probably the most widely used tool in practice. It lets you visualize two parameter fibroid barcodes, but it does struggle with large data sets. This is running an O of n to the 8th, where here n is this is if we're looking at 0, right? So this computational cost right here is if we're looking at n data points in n points, and we're doing zero-dimensional homology here. So this lets us compare Rivet with the elder rule stair codes algorithm, and we can see the elder rule stair codes is much faster, but also much less specific. Now, multi-parameter persistence landscapes are built off of the fibroid barcode. And so these are not going to be faster than Rivet because, at least, Rivet is the most commonly used tool for computing these fibroid barcodes. So these multi-parameter persistence landscapes algorithms sort of depend on Rivet to work. And multi-parameter persistence images are generally faster to compute than the fibroid barcode. And you might be asking, how does that make sense? Because they're sort of based on the fibroid barcode. The idea is that with these multi-parameter persistence images, oftentimes you're not looking at the full fiber barcode. You're not looking at all the lines. You're just looking, you're okay with losing some information. So you pick a resolution, like how close are these lines going to be together? And you lose information, but that's okay sometimes. Yeah, so to summarize, multi-parameter persistence is a pretty hard problem. There's no clear-cut answer, like the one parameter case. Yeah, but even though we don't have like this great complete discrete invariant, we can still compute invariants that lose information. The most widely used invariant is the fibered barcode, also known as the rank invariant. The fibered barcode is stable to noise. And then there are also a couple invariants built off of the fibered barcode, persistence images and persistence landscapes. And these are also useful for machine learning and statistical applications. And then the elder rule stereo is the best bet for zero-dimensional homology with augmented metric spaces. So here are some references if you want to look at any of these topics further.